Now in this question, they ask you what are the conditions that are needed for the waves to interfere. So for the three conditions, number one, they must meet at a point. Alright, number two, they must be same type of wave. And number three, they must be polarized along the same plane. And then the next part, they give you a two-source interference experiment using light. And they ask you to suggest a suitable separation of the slits of the double slit here. Now for light, right, you need to know that the range that is acceptable will be between 0.3 to 3 mm. So it's something like you've got to memorize this lah. So you write any value between these, for example 1 mm, then you are fine. And then the next one is quite straightforward, writing down the expression between lambda d and x and a. So it's lambda equals to ax over d. Now for the next one, they ask you to determine the effect, right, on the separation of the fringes and also the maximum brightness when you change this. So when you double the d, right, d being the distance from the double slit to the screen, let's use this formula as a reference, x equals to lambda d over a. So you notice that when d is doubled, your x will be doubled. Now because they specifically mentioned 2d, your value here must also be specifically 2x rather than just increases. So here you would say the separation increases to 2x. Alright, and what about maximum brightness? Now you can imagine this, right? If you place the screen further behind the source, of course by the time the light reaches there it will be less bright because it'll travel further. So that's why your maximum brightness will be decreases. Now next one, the wavelength is increased to 1.5 lambda, keeping a and d constant. So once again, we look at the lambda here. If it increases to 1.5, your x will also increase to 1.5. So here you can say increases to 1.5x. And what about maximum brightness? Now this one you have to know a little bit about the effect of diffraction. Because we are talking about when a light, right, passes through a gap, it undergoes diffraction. So something like this, let's say this is your slit, and let's say the wave, alright, this is the wavelength and this is the size of the slit. Now in the size of the slit is equals to the wavelength, you get maximum diffraction. But when the gap here is much bigger than the wavelength, then very little diffraction occurs. And when the gap is smaller than the wavelength, the wave will not be able to spread. After that you will get like very little can pass through, so you get blocked off, sort of like it's blocked off lah. So therefore the condition for diffraction to occur is the gap must be either equal or larger than the wavelength. So let's say we have a particular situation where the wavelength initially lambda is much smaller than the gap, so it will spread very little or very little diffraction occurs. But when you increase the wavelength, so now it is much bigger, so let's say it's almost similar to the gap. So what will happen is it will spread even more. So imagine when the light passes through each slit, there are two of these, it spreads more. Alright, that means the energy, right, will be spread out over a larger area. So therefore the light from each slit will be less bright. So therefore your maximum brightness also will be less bright. So you can say maximum brightness decreases. And the last one, the intensity of the light incident on the double slit is increased. So when you increase only the intensity, we notice that has nothing to do with any of the terms here. So therefore the separation remains constant. When the maximum brightness though, now intensity of the light, that means each slit has a larger intensity or brighter. So therefore when they meet, your maximum brightness will also be brighter. So you can say maximum brightness increases. Now in this question, they gave you white light passing through the double slit. So what would happen? So the single slit here is so that the light will spread over a larger area and is able to cover both slits lah. So when the light comes out, it's still white light here. So what will you see here? Now remember, white light isn't a white color by itself, but rather it consists of all the 7 colors. So what I'm saying is you can treat white light as having 7 different colors, and each color that emerges will form its own pattern here. Example, violet being the shortest wavelength. If you use the formula x equals to lambda d over a, so shortest wavelength will give you the smallest x. Now you need to understand, when the x is small, it means the separation between them is small. the size of the slit is also small. As like you look at this, so let's say this is the violet that I'm drawing here, the violet here. So it has a very narrow slit, the size of the slit is small, and the separation is also small. So this will be the pattern for violet. Now then, if we do the other end, which is the largest wavelength red, now red being the biggest or longest wavelength will have the biggest X. So what that means is not only will it be further apart or furthest apart from each other, the separation of the fringes, but each fringe will also be thicker or wider. So it's a larger fringe here. So what you will notice is what I drew for you is only the pattern for 2 colors. We haven't even done the patterns for all the remaining colors. But imagine we will do the pattern for the remaining colors, each having different fringe spacing and also different fringe sizes, some narrower, some wider. So what you will notice is they will overlap sort of like not in a fixed arrangement, all right, not a fixed pattern. So what you will notice is in the middle though, all the colors will give you a bright fringe. So therefore all the colors will mix again to give you white. So the central fringe will be white, but all other places they'll be mixing in different sequence because they have different fringe spacing and also different fringe width, right? So they will overlap sort of like more jumbled up like that. So therefore you just be colored fringes. All right, so the answer would be central fringe is white with colored fringes on each side. So finally, right, the pattern will look something like this. Okay, so that's what I'm going to show you. This is how it looks like in real life. Right, the next one, they mentioned that again, this is a Young's double slit experiment. So the first part is quite straightforward. They give you all the information and you just have to find the separation of fringes, which is X. So substitute all the values, but be careful to convert any millimeters to meters, then you'll be fine, right? And also nanometers to meters. Right, after you have found the answer in meter, don't forget to convert it back to millimeters. All right, but you cannot say, oh, since the answer is millimeters, so I'll leave it in millimeter. Now you can't do that. The moment you convert one to SI unit from nanometer to meter, then everything has to be in SI. Then only you convert it back to millimeters. Right, the next part, state the effect, if any, on the appearance of the fringes observed on the screen when the following changes are made separately to double slit. So number 1, the width of each slit is increased, but the separation remains constant. Now, if you notice, right, they are saying that the width of each slit. So let me just show you how it looks like. Now, imagine this is the width of each slit, right, the gap here. So I'm making it bigger. So can you see this gap? I make it bigger, and this gap I made it bigger. But I'm maintaining the separation. So how can I do that? Now, separation of the slits is always measured from center to center. So even though now my slit is wider, but the center to center distance is still the same as before. So that's what they're talking about. So what will happen to the appearance of the fringes? Now, appearance of the fringes would refer to the separation of the fringes and also the bright and dark fringes, darker or brighter or no change. So let's first talk about the separation first. Now, since your A, right, which is the separation of the slits, are basically the same, so therefore there will be no change. So if A is the same, X is the same. So the first part is the separation of the fringes is unchanged. Now, what about the bright and dark fringes? Will they be brighter or darker or no change? Now, I want you to imagine that when you increase the size of each slit, now more light can pass through compared to a narrow slit like this. Right, this is a narrow slit. So if it is a wide slit, more light can pass through. And also you must realize that there will be less diffraction occurring because now the gap will be much bigger than the wavelength. So my point is, more light will pass through, it will spread less. More light will pass through, it will spread less. So basically, when the light comes out, they're actually brighter than before. So when they meet to form constructive interference, the bright fringes will also be brighter. So that's the second point. The bright fringes will be brighter. Now, what about the dark fringes though? Now, if you imagine, right, the dark fringe being formed when a peak from this slit meets the trough from this slit. Now, since we already said the light coming here is brighter, so it's a bigger amplitude than before. Maybe before there was small amplitude, now it's a bigger amplitude. Similarly, from this slit initially was small amplitude, now it's bigger amplitude. But for destructive interference, the peak of this wave must meet the trough of this wave. Since they are both equal amplitude, even though they are both bigger, but they will still be able to cancel out perfectly. So therefore, your dark fringes will remain dark. All right, so there'll be no change to your dark fringes. So that's your third point, the dark fringes remain dark. Now, the next one, the separation of the slits is increased. Now, if you remember that the formula for x is lambda d over a, so when we increase the a, obviously the x will decrease. So that's the first point, the separation of the bright fringes decreases. But what happens to the appearance, which is the bright and dark fringes, brighter or darker? Now, for this case, right, it's very unique because I want you to look at this diagram which I drew. So initially, these are your two slits. This is the separation between them, center to center. Now I'm increasing the separation from center to center, but the size of each slit remains the same. So my point is the same amount of light passes through here than before, same amount of light passes through this slit than in the previous slit. So the amount of light passing through and spreading are basically the same as before. So when they overlap, even though they have a smaller overlapping area compared to this, but the overlapping area would still be the overlap of two waves which are the same amplitude as before. So therefore, the bright and dark fringes will remain bright and remain dark respectively with no changes. Right? So the second and third point will be the bright fringes will remain bright and the dark fringes will remain dark. So as a final summary, remember in the previous question, I think 2 questions before this, we talked about changing the lambda and the d, how it affects the x and also the appearance. So the x and d will obviously change the x and also change the bright fringe, whether it appears brighter or darker. Alright, but for the a here, it will only change the x, which is a separation, but it will not affect the brightness of the dark fringes and the bright fringes. So this is the exception. You change this, you will only change the x, it will not affect the appearance of the bright and dark fringes, as in that brightness. Only lambda and d will affect the brightness. So you must remember this. Right, for this question, they gave you the wavelength and the fringe separation. All right. So what would happen when you are using a different wavelength, which is basically halved, and you double the slit separation? Now this is a pair of slits, so this will be Young's double slit experiment. So obviously the formula that you would have to use will be x equals to lambda d over a. So let's make x as a subject here because we want to find the final fringe spacing. Now what is the same though? Now they did not mention anything about changing the big D, so that will be constant. So when you're using the ratio method, it will be x2 over x1 will be simply lambda 2 over a2 divided by lambda 1 over a1. Alright, this one no need to write because it will cancel off. So then you can cross multiply and group them together, so you get lambda 2 over lambda 1 times a1 over a2. Now you substitute the new wavelength and the original wavelength. Now they didn't tell you exactly what's the a, but they did tell you the slit separation is doubled. So a1 over a2 is 1 over 2. Alright, that's enough. So you get 1 over 4, and don't forget to bring your x1 over if you want to find the new fringe separation. So bring your x1, which is 3 mm over, so then you will get 0.75, which is a. Now for this question, I'm not going to spend too much time on a and b because we have done similar questions like this in the previous question. The only thing I want to tell you is if they ask you to estimate the separation of the dark fringes, it is basically the same as finding the separation of the bright fringes, because bright and dark fringes, right, separation of bright fringes will be the same as the separation of dark fringes. So use the formula x equals to lambda d over a, and as usual just substitute the values. Now this one is the one I discussed because they say initially the light passing through each slit has the same intensity. So then the intensity of light passing through one of the slit is reduced. So what will happen to the dark fringes? Now let me just tell you overall what happens. Now you did not change any of the parameters like lambda, d or a, so of course the separation wouldn't change. Now what about the bright fringes then? Now, they didn't tell you which slit has the lower intensity, but it doesn't matter. If one of it has smaller intensity, let's say the top one, that means the amplitude from this slit will also decrease. So when they interfere constructively, initially these two have the same amplitude, but if one drops, they will still add up together through the principle of superposition to give you a larger amplitude, but it will not be as big as before. So definitely the bright fringe will be less bright. Now, at the same time, right, the dark fringe, right, that is formed, remember it is formed when the peak from this slit meets the trough from this slit. So now that they have different amplitudes, maybe this one is smaller now, but the trough here is bigger than the peak. So even though they add, right, you won't get perfect cancellation. So instead of completely getting dark fringe, you will get slightly brighter. So then here you would have to tell them what will happen to the dark fringes observed on the screen. So you would say that the separation of the dark fringes will remain the same, but the dark fringes will become brighter because the resultant displacement will no longer be zero, as the displacement of the waves will not be able to cancel out each other. Right, the next one, they ask you that which changes can make the distance between loud regions reduce. Now, the distance between loud regions is basically the x, right? The separation of the bright fringes in light, but for sound is separation between loud and loud, because the loud represents constructive and the quiet represents destructive. Right, so let's look at the formula. So if you were to write down the formula, which is x equals to lambda d over a, so let's see which change, okay, will cause the x to reduce as well. By the way, the d here, which for Young's double slit experiment represents the distance from the two source to the screen, here would be the same distance here, d, which is from the two stickers to where you are observing the pattern of constructive and destructive. So you can actually change this to small d if you want to, it's the same. So let's look at the first change here. So if you were to decrease a, right, make it smaller, x will be bigger, but we want it to be smaller, so that's out. Now increasing the distance d here, which is here, would actually be increasing it, so the x will increase, so that is also wrong. Now increasing the frequency of the audio frequency. Now you may think, oh, frequency is not involved here, right? But actually the frequency will affect your wavelength. From the formula, v equals to f lambda. So from the formula v equals f lambda, you will notice that v will be constant in the same medium right speed of sound, even though the frequency will change, but v will be the same. So lambda will be equals to v over f. So v is constant. When f increases, you notice the wavelength will decrease, and if the wavelength decreases, then obviously your x will decrease, so your answer will be C. But just to check whether D can be possible or not, now they said you are just increasing the power output. Now what will happen if you increase the power output from the source here? Basically these two will be louder. So what will happen is the loud will become louder, but the quiet region will stay quiet. Alright, because it doesn't matter that the amplitudes are bigger, but they will still cancel out each other here.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.